take a minute. This worked really well last unit. Most of you got above 80%. So take a few minutes. One of these problems, you've seen one very similar to it. It's not the exact same answer, though, because the numbers are different. But take a few minutes, discuss. From the Christmas assignment, you should be able to do both of those questions. One's hard and one's very simple if you know how to do it. Dependable. All right, so here we go. This one was very similar to number 5 or 6, I think, on the test. So we had 2s O2 plus O2 goes to 2SO3. I actually have it on the next page, a lot bigger. And it says, all right, the reaction is going to happen. It's at room temperature, so the 298. What's the pressure after? So we have to know chemistry before we can do math, and I know that sometimes that's the struggle. But it tells us here we have 0.4 of this and 0.4 of this, correct? So this is actually a limiting and excess reactant problem from chapter 4, which you didn't love them because they're complicated, but this one's not that bad, hopefully. So you look at the coefficients. Here's a 2. This one has a 1, right? So you ask yourself, is this number 2 times bigger than that number? No. So that means SO2 is your limiting reactant, correct? Are you okay with that part? All right. And it also means this 1, it means you use 1/2 of the O2. It's a 1 to 2. All right? So the 0.4 is cut in half. So it's 2.2 excess of O2. Who's okay with that part? A handful of you. All right, and then the nice thing is since this and this have the same coefficient, that's supposed to point to the 2, then the amount of this consumed will be equal to the amount of that created. All right, so this went to 0, so this must go up 0.4. So the total moles left at the end are 0.2 of O2 plus 0.4 of SO3. So we're looking for the one that has 0.6 because everything else is a constant, right? So how many were successful with that problem? It's a tricky. We got 4, 5. All right. It is a little bit hard. But hopefully the concept is something you're okay with. So you have it on video here. You have it on video on the Christmas assignment. It will be on your test. All right? It won't be number 7. And I'll probably change these numbers just so you have to not just memorize the answers C. All right. Then, a partial pressure. When you came to this problem, hopefully it was after number 4, right? So you're like, well, that video is only 2 minutes long. That's going to be a lot better than 17. Partial pressure isn't too bad. And this one, you can think through this one if you've done them enough. But partial pressure is equal to this goofy-looking X, which we call the mole ratio. Oh, my. I took Christmas break off, and my handwriting got worse. All right? X is the mole ratio, and you multiply it by the total pressure. All right? Let's see. Now, this one, I wouldn't do any of this, but I will do it this way to help explain the process. All right, so I'm looking for just argon, right? So the mole ratio means moles of argon divided by total moles. All right, so I take my moles of argon, which is 0.2, and how many total moles do I have? 0.5. Okay, that's the 0.2 plus the 0.1 plus the other 0.2. So I end up with 2/5, essentially. Are we okay with that? Now, I'm going to take 2/5. That's my mole ratio of argon. Or if you want, 0.4 is just fine. All right? And I'm going to multiply that by my total pressure, which is 5. Are we okay with that? So the 5's cancel out, and I'm left with 2. Okay? Hopefully it wasn't too bad. And hopefully this is a problem that as you can read it, you can see the moles add to 5, and you can, or 0.5, and the pressure is 5. So you can do the math, or this one you can kind of notice, well, if it's 0.2 of 0.5, it's just 2/5 times 5. All right, who was able to do that one? Raise your hands. That's more than 5. That's a good sign. Okay. Partial pressure. Definitely going to be assessed in more than one way. Okay? Mole ratio times total pressure. Had we done mole ratio before in any other? Okay. We'll use it again. It's probably chapter 11 or chapter 13 where it comes up. But it's very common. This is called chi. It's just Latin, and it's an X. Okay? In case you read it. What's that? Sounds good. All right. Today, more Pivner, but we're not going to do a ton of math. We're going to actually derive it. So here we go. If you want to take notes on this part, you can, but you don't. Nothing today will be on the test besides what we just did. So this is just the first few sections of chapter 10, which maybe you read over the break. I'll just pretend that you did because it's 2019 and that's what you do, right? You are amazing. Did you enjoy it? It's not that bad, right? The first 3 sections of chapter 10 are only like 3 pages. So it's fast. That's okay. So you like math? Okay, that's fair. All right. So there is actually something on the test sort of from the slide. And you don't need to write it all down. Just think about your experience with gases like in a balloon. Gases are unlike liquids and solid. They first expand to fill their container. That's actually a weird thing. Like, we're used to it. But I have, like, these pieces of magnesium here, and they don't expand to fill this tray. They just sit there, right? Gases will spread out and fill their container as much as possible. All right? They are highly compressible. That means you can squeeze a gas because there's room between their molecules to make them closer. All right? And they have extremely low densities. Let me pause this and put Cade to work for a second. So the test question that does come from this slide and kind of the conversation and hopefully the common sense that you understand about gases, it will say, which of the following is false about gases or something like that. And it'll be like, they fill their containers, they're compressible, and they have high densities. You just pick the one that's a lie. So, like, it's not a hard one, but just read them all, because it might be tricky because one of them sounds true, but it has one word that's wrong. All right. Now, we're going to talk a lot about pressure. We're going to do 2 labs. One will be tomorrow. But pressure is just simply the amount of force applied to an area. You don't need to know like how we derive it or anything like that. But know that 1 ATM is equal to 1 atmosphere of air on top of us. That's literally what it is. Because air does have mass, whether we think it does or not. It does. All right? And we have roughly, 50,000 feet of air above us. Mm-hmm. It's a very small change in pressure, but your ears definitely feel it. And they're used to where you live. And you go up, the pressure gets less, so now your head's like going to explode out your ears. And then when you come back down, then it's more, and it hurts. I give driver's ed kids whenever I go to Logan. Not all of them, but they're like, "Wow, my ears won't pop." Toughen up. All right. Whatever. Okay. We won't use pascals, but pascals is a unit of pressure. Bar is a unit of pressure. We don't really use those as much either. We use atmosphere and torr. So millimeters of Hg or torr. These are the same thing. All right? So you do need to definitely know that if you read millimeters of Hg, it means torr. So it also then means this, because this, I used this a few times in the Christmas assignment videos. This is a conversion that you definitely need to know. It is something, if you want, you can put in your calculator. I don't know. So to go from torr to ATM, we have this 760 to 1 ratio. It's not too bad. Now, how that actually literally comes is from the pressure. It pushes on an amount of mercury, and that pressure will push the mercury up and down in this vacuum tube. All right, that's literally how they measured pressure back in the day. When you watch the news, they'll usually say something like 30.23, and they're talking inches of Hg. We're in America, so we use weird things like inches, feet, and Fahrenheit. But whatever, it can be converted to torr through the 2.5 centimeters per inch, but you don't have to do that. But yep, room temperature is 25 C. All right. So then we don't really care about a manometer, but it's another way to measure pressure. You have a reaction happen here. All right, this will go up and down based on the pressure inside of there. We won't, well, we'll sort of use the manometer, but not really. All right, normal atmospheric pressure is equal to 1 atm or 760 or 101.325 kPa. That would be kilopascals. You do not have to have that memorized, but you may see it, especially in physics. Physics actually uses pascals, most common in pressure, but we don't in chemistry. All right, Boyle's Law. I like that because my mom's mom is a Boyle. All right, says the volume of a fixed quantity of gas at constant temperature is inversely proportional to the pressure. All right. Now, you don't need to know these laws, but there's going to be 3 laws that help us to know PIV-NERT and why it actually is the way that it is. And if you didn't watch any videos, and if you weren't here the last day, PIV-NERT is what we call the ideal gas law, and it has 3 variables, P, V, I guess 4, N, and T, and then we have this weird constant. So the first that we're talking about is Boyle. It says, and we're okay with this. It says if you apply pressure, the gas volume is going to get smaller. So if you squeeze a balloon, the balloon gets smaller. Everyone should hopefully be okay with that, right? So if I have a large amount of pressure, what type of volume do I have? I have a low volume, right? Whenever one goes up, the other goes down. We call that what type of relationship? Inverse relationship. And on a graph, an inverse relationship would be something that you would ski down instead of something you would climb up, right? It would point down. Okay? So volume and pressure are inversely related. All right, next. Well, there you go. I just said all this. Don't worry about this PV equals K stuff. We'll talk about K. It's going to turn into R, but whatever. So a plot would look like this, or it would go down, or an inverse plot would have a line that pointed up. That just is proof that it is an inverse relationship. All right. Charles' Law, which is cool. That's my grandfather's name. No one cares. All right. Well, if I'm going to talk about my mom's, that's my grandma, huh? Whatever. Moving on. Anyway, here we go. Charles discovered that the volume of a fixed amount of gas at constant pressure is directly proportional to its temperature. So this would be why your balloons, if you lock them in your car, in the summer, they can pop because the pressure is still 1 atm, but the temperature gets hot, so the balloon has to get bigger, and that can sometimes make it pop. So as temperature goes up, so does volume. We call that a direct relationship, and on a graph, the arrow would point up. Yeah. It can, a tiny bit. But if we think about the atmosphere and the temperature at the ground versus the top, they're so drastically different that we wouldn't really worry about the changes in temperature in the atmosphere. Good question, though. All right, so far we all right? All right, then I do not have anyone related to me with the name Avogadro. But that would be cool if I did. Yeah, you would. All right. Avogadro said the volume of a gas is dependent on how much there is. And that one's super obvious. The more stuff, the more it's going to take up space. All right, so mathematically, that meant the volume, and when I say equal signs, these are like proportional signs. So it should have been like a whatever. But I did that with my mouse, and squigglies with a mouse are harder. So mathematically, if they're directly proportional, once again, we have one that goes up. Okay? More moles, more volume. Okay, so here we go. That green turned out to be a lot uglier than I thought it would, but that's okay. So we have the relationship between volume, pressure, N, which is the amount of stuff, or the moles, and temperature. And I want you to notice that this is pretty cool. These arrows will set up this equation for me. It says that volume, and once again I should use squigglies because it's not exactly equal to, it's proportional. These two arrows that point up mean that these two variables are on the top of your equation, N and T. Since the blue one, which represents pressure, is pointing down, that means that that variable would be underneath. All right? And now we have this equation that says my volume is roughly proportional to the amount of stuff I have times my temperature divided by my pressure. So V equals N times T over P. Now, these are all fine and dandy, but we don't want just they're sort of equal to. We want an equal to. So to make all of these things talk to each other, they came up with a constant, and they call it R. And I don't remember why it's called R. There is a reason. But R has the units of moles, temperature, and pressure. It makes all three of the things talk to each other. And R is equal to 0.08206, technically. All right? Which sometimes is 206. 0.08206. So it's 0.082, as you saw in that AP test question, or 0.0821 is what I usually round it to. That's it. That was easy, right? Okay. All right. So what we do with R to make them talk is we put it right in here. So V equals N times T times R over P. Now, that can be arranged whatever way we want, but typically this is written, and you just memorize piv nert. I take P over here. I have P times V equals nRT. This is the ideal gas law, and it is extremely important. Chapter 10 is all about the ideal gas law, and you'll use the ideal gas law in probably 90% of the problems on the exam. The nice thing about PivNert is it's just math. Someone in here said they've discovered they don't like chemistry, but they don't mind math. Those kind of people might like Chapter 10. Someone I talked to just yesterday said they hate math, and so Chapter 10 might not be very fun. So, anyway, this equation, you have to know how to use it to solve for any of these variables. T is always a constant. N is always a constant, so we don't have to solve. I gotta shut up. R is always a constant, so I never solve for it. I solve for the other four. That'll be fine. I was told this weekend that people love to see when I screw up. It makes them happy. It's like, that hurts my feelings. All right. So here is a sample problem. I don't think I gave you any like these on the Christmas assignment. So please work this through with me. It says, what volume of gas will be produced when 25 grams of sodium carbonate reacts with 200 milliliters of 3 molar HCl? So there's some chemistry involved here. All right, it gives you the temperature, it gives you the ATM. So the first thing you need to do is chemistry. So sodium carbonate is Na2CO3. When it reacts with an acid, your little red flag we learned forever ago was carbonate, right? When you have carbonate and it reacts with an acid, it creates the metallic chloride, so NaCl, plus water, plus carbon dioxide. And there's your gas. Okay? So since we're in piv inert, we really only need to care about the thing that's a gas at the end. So I need to find, this piv inert has an N in it, I need to find moles. Go ahead. No. If the problem, most of them will not have you deal with water vapor, because that complicates it. If I gave you a thing here, that the partial pressure of water at 30 degrees Celsius is 0.21 or whatever, then yes, you would have to worry about it. If you're not given the vapor pressure for water, you do not have to include it in the problem. All right, so I need to balance this, because chemistry always requires you to balance. There's 2 Na, so I put a 2 right here. All right, that makes 2 Cl, so I got to put a 2 right here. That makes 2 H's. There are 2 H's. So then I check my O's. There's 3 here. There's 1, 2, 3. So I'm really good to go. 1, 2, 2, 1. Now this would be nice if you forgot to balance this. It wouldn't even matter, because there's a 1 in front of your gas, and there's a 1 in front of the thing I'm giving you here. All right. So, well, maybe it would actually. So now we need to use 25 grams. It's going to react with this volume of this molar. So I got to convert this to moles. Okay, we've done this before, and that doesn't always mean that it you feel good about it. 200 milliliters is 0.2 liters, correct? You okay with that? Times 3 moles per liter, so it's just 0.6. Are we okay with that? All right, so I have 0.6 moles of HCl, and then I have 25 grams of sodium carbonate. So I need to take 25 grams, and I need to find the mass of sodium carbonate, which is 46. This is, I'm pretty sure it's 100. Does anyone have that? Hey Siri, what's the molar mass of sodium carbonate?
The answer I found is 105.965
Oh, I was way off.
atomic mass units.
So 106. I went wrong somewhere. All right, 106. And we end up with what's that? 0.25 moles of NaCO3, Na2CO3. Is that not what you said? That's what I wrote. Ooh, how am I going to lie here? There you go. 0.24. It's right there. All right. So why did I have to convert both those to moles? That's true. I need to find out which one is going to determine how much gas is produced. Limiting reactant always determines the amount of product produced. So I need to know. All right, right here is, I'm going to ask this the same way I've asked this a lot. So I have 2 here and I have a 1 here. Is this number at least 2 times bigger than this number? Yes. So that means which one is your limiting reactant? That means this is your limiting reactant, right? Okay. Now the math from here isn't that. The math from here is not that bad. If you'll look, for every one of these consumed, how many of these are made? 1. So the amount of carbon dioxide produced is equal to the amount of moles of Na2CO3 that I started with, which is this number, right? 0.24. Make sure I don't write 0.25 again. All right. So now, in the end, I now have 0.24 moles of CO2. And then from here, it's not bad. We're solving for, is it pressure or volume? Volume. So if PV equals nRT, volume will be equal to nRT over P. I have 0.24. What's R? 0.0821. The temperature, did anyone write that down? Okay, so 298. And it was 0.97 was the pressure, correct? Is that right? All right, I saw this number, and I didn't even look. That's the grams. It is 30, I'm sorry. I just saw 25, so I put 298. So yes, 303. Thank you for calling me on that. 303.97, is that what it said? Did a roll. Anybody get an answer? What's that? 6.63, and that would be liters, because I'm solving for volume. Uh-oh, something different? 6.15? Uh-oh. Oh, I already had that. 6.15. More people got that than 6.63. All right. These questions, they are complex. It's all about your ability, typically, to find N in your PIVNERT. Because that's where chemistry can happen. That's where reactions can happen. That's where balancing comes in. That's where stoichiometry comes in. So definitely, I know that they're tricky, but they're doable. Okay? This is a question that was from a lab on the AP test a bunch of years ago. All right, now you didn't do the lab, but you read about it, you got the results, and one of the questions, one of the parts was this. I think the next one's exactly the same. So the only thing different here would be to do what? All right, you would have to convert this to ATM by dividing by 760. Okay? Okay, that's not bad. So coming back here, if this was a 2, then you would just double that number or half it or whatever you need to. It's just basic math on that. All right, you don't have to do this problem. I'll leave it up there. The bell rings soon. Well, when does it ring? It's a pretty good deal for a family. We can get out of there for under $50 sometimes. All right, the constant of proportionality, known as R. By the way, kids ask me all the time, why do you capitalize P, V, but not N, R, and T? I have no idea. It doesn't matter. That's not in a book. That's nothing. That's just Tom Davidson. Did that bug you, Kitzel? Were you bugged by that? Oh, okay. Here we go. Now, you do need to know that R does have other values. Now, this sounds weird because it's a constant. These are all the same value. That sounds weird, but they're for different units. We never use these. But in a different chapter, we will use this one. All right, but don't write it down yet. But do know that R, even though it's constant, depending on the units, it will have a different numerical value. Yep. So we use this when we get to chapters 19, I think, when we talk about energy. There's more than that. Merry Christmas. All right, now, one of the ways that we deviate, or we expand, I guess, I don't know, from the ideal gas law, this was in those problems, and I said, hey, we'll talk about how we get this equation in class. So we can find the density of a gas through the ideal gas law. It's pretty cool, and you can see that it is very important. If we divide both sides of the ideal gas equation by V and by RT, we can arrange it this way. So N over V is equal to P over RT. Now, there's nothing fancy here. We just rearranged it. Are you okay with that? All the parts are still there. We just algebratized it. If you'll notice, N over V is moles over volume, which is sort of close to density. All right? So, moles over volume is now going to be equal to, that's an M, sorry. I didn't skip a slide, but it wasn't there. All right, so here we go. We know that moles times molecular mass is equal to mass. So if I have moles and I have gram per 1 mole, this cancels out. I'm just left with grams, right? So that's what this is saying. My grams per volume now is equal to pressure times molar mass, which is how we got this to cancel out to just be an M instead of an N. All right? So we can rearrange this. We can say density is equal to M over V, and really, if I get rid of this for a second, I can now then say the density is equal to PM over RT, where capital M is your molar mass. It's a pretty slick way of finding the molar mass of a gas. Even if you don't know what the gas is, we can use what it is. All right, so note, only one needs to know the molecular mass, the pressure, and the temperature to calculate the density of a gas. Okay, and we'll call that good.